And I'm a PhD student in geology here at UTEP. And today I'm going to be talking to you about my summer internship that I did at NASA last summer, entitled Topographical Analysis of Fretted Terrain, Implications for Ancient Martian Supereruptions. And don't worry if you don't know what the term fretted terrain means, I'm going to explain that. But just to give you a little bit of a hint, the image that's behind the text there is fretted terrain. So just a little bit of background on Mars to kind of set the scene. It's currently dominated by wind erosion, but in the past there's a lot of evidence for type erosion like fluvial erosion and glacial erosion. So that's just something to keep in mind while I'm giving this talk. So why should you care about volcanic processes on Mars? So volcanoes hold a key to the history of the atmosphere on Mars and therefore the potential for past life. So volcanoes erupt, put gas into the air, the gas allows the atmosphere to heat up, and that allows for a greater potential for life. And so this is just an artist's renditioning of what Mars might have looked like back when there was a larger atmosphere and fluvial activity. And also, there's currently a gap in our knowledge of where all of the volcanic deposits that we see on Mars came from. We haven't identified enough sources to know where all the volcanic deposits came from. So that's another reason why this research is important. So here's an image of Mars. For those of you who might be familiar with Mars, up here is Tharsis Montes, which is home to the largest volcano in our solar system. It's about the size of Arizona, called Olympus Mons. Over here is Valles Marineris, which is the Grand Canyon of Mars. And then my study area is up here in Arabia Terra. So up here is Arabia Terra in this box, and so how my research began was in 2013, two scientists, Mikowski and Bleacher, published in Nature, and they found these circular depressions that were previously thought to be impact craters. So here, these circles here, these are impact craters from like asteroids or something hitting the surface and creating a circular depression. But upon closer inspection of these circular depressions outlined and dashed in white, they realized that they had more of a morphology similar to these explosive calderas. And so over here is a zoomed-in image of one of these explosive calderas, and it is an elevation model, so red is higher elevation, blue is lower elevation. And this is just to show you what these calderas look like, and I'm going to explain what I mean by caldera. So these type of volcanoes aren't your traditional volcanoes that you might have made in high school or at a science fair. Rather, these are these super explosive volcanoes. So this is an artist renditioning of what the Yellowstone eruption might have looked like. So super explosive. And this is Akiak caldera up in Alaska. And so this is what Yellowstone would have looked like pretty much right after it erupted. Because these volcanoes are so explosive that the magma just leaves the chamber and then the surface collapses and you get this big hole in the ground. So you can kind of see how this resembles what they were seeing. And so to give you another idea of how explosive these volcanoes are, here's a map of the ash thickness from the Yellowstone eruption. So Yellowstone is right here inside of this blue circle, and as it goes out to yellow it gets thinner, but pretty much the ash deposits from the last Yellowstone eruption about 600,000 years ago covered the entire 48 contiguous states. So again, here is Aden Patera, which is that caldera I was telling you about, and it's located right here. And another weird enigma about the Arabia Terra continent on Mars is this deposit outlined in white here called the friable deposit. So scientists for a while have thought that this deposit was volcanic in origin, but before 2013, they didn't have a source. But now that we have a source, my research is reinvestigating parts of this deposit. So here's another image of the deposit. This is an elevation model. Red is high again, blue is low. And outlined or colored in red here are these suggested supervolcanoes or calderas. And this is just to show you distances from those calderas. So the part of the Arabia Terra deposit that I'm interested in, or that my research focuses on, is called the fretted terrain. So fretted terrain is outlined in this black polygon here, and I'm going to go into what fretted terrain is. So here's an image of the fretted terrain, zoomed in. And just for scale, this is about 25 kilometers. And so what I want you to see is that outlined in this red polygon here, there's these high-standing mesas, and then in the yellow are these low, deeply carved valleys. And so that's what is indicative of the phoretic terrain. And scientists don't know why it looks the way that it looks, or why it is this way. So that's part of what I'm investigating. So here's a zoomed out image of the phoretic terrain. That's 90 kilometers there. Again, this is an elevation model, so light colors are higher elevations, dark colors are lower elevations. And you can kind of see, again, these polygonal high stands and these low cutting valleys. And so my question became, are these valleys gravity driven, or rather are they fracture driven? And so by gravity driven, so this is an image in New Zealand of an area that the valleys are gravity driven. So they're carved by glaciers. So glaciers want to go downhill. So that's what I mean by gravity driven. And then over here, this is the San Andreas Fault in California. And as you can see, these rivers here, normally if this fracture wasn't here, they'd just continue to go downhill. But instead, because this fracture is here, they want to follow the fracture. So that's the question that I'm addressing in my research. So here's a map that I made of the valleys that are in this like chartreuse color. And again, this is an elevation map. And I can go into later about how I got these valleys, but I won't because I don't have enough time. But here are, the first thing that we noticed when we looked at these valleys was they have a very distinct, what's called drainage morphology. So here are the four main drainage morphologies that we see on Earth. But the two that I want you to look at particularly are this rectangular pattern and then this dendritic pattern. So the dendritic pattern is what you might expect to see on Earth, right? That looks like kind of, if someone to ask you to draw a river, you might draw something that looks like that. But what we're seeing in Arabia Terra is this more rectangular pattern, which indicates joints, faulting, and some kind of lack of regional continuity. So something besides gravity-driven erosion, which is what you would see in this dendritic pattern, or maybe the parallel pattern. So then we decided to investigate that a bit more. So this is just to give you an idea. This is going to help you with the next figure that I'm going to show you. But this is just to give you an idea of the way that you would expect the valleys to be carved if it were gravity-driven. So you would expect the valleys to go down slope. So that's what these arrows are showing you. They're showing you the way that you would expect to see the valleys to be carved. And so let's first focus on, these are called rose diagrams. So imagine like north is up here, south is down here, you got east and west, and the purple are my measurements, my orientation measurements from the valleys that I created. And yellow are the primary slope direction that I was showing you in the previous slide. So what I want you to see here is what you would expect to see is in this rose diagram where all the purple kind of mostly follows the downslope direction. That's what you'd expect to see for a gravity-driven erosion. But rather what we're seeing is some kind of bimodal, so two main directions. And the one main direction is against what you would expect for gravity-driven erosion. So this is what we're seeing in my study area. And so what that indicates is that yes, it is some kind of fracture-driven. So then the question becomes, what caused the fractures? So we have three main hypotheses that I'm going to touch briefly on. So the first one is, so this figure kind of goes in a U shape, so I'm going to walk you guys through it. So first, you have this valley that is carved in the downslope direction as you would expect. And then here you have this ash deposit or lava deposit on top. And as it starts to cool on the top and on the bottom, it contracts, as you'd expect something hot to do. And you get these fractures. And these fractures form, and then instead of carving down slope, the erosion processes will preferentially carve through the fractures, which is how we might get these fractures that are oriented perpendicular to slope. So that's just one of the hypotheses. So the second hypothesis is what we see in a place on Mars called Tractus Catina. And so these all here are low areas that are grobens or just low stands in the topography. And these grobens are caused by dike intrusion. So here is this rectangle is supposed to represent a dike, which is just kind of magma that injects into the surface, and rather than coming all the way up to the surface to make a volcano, it just kind of sits right at the bottom of the surface, and you get this tension. So it starts to pull apart, and you get these gravins. So that's what is happening, or what scientists think is happening in Tracus Catina could also be what's happening in the fretted terrain. So then the final hypothesis that I have is that something similar to the chaos terrain on Mars, where in A, you have a low standing area that's filled with ice, and then it gets deposited on, and then the ice starts to melt for some reason, either climate warming or maybe magma comes up and starts to warm it, and then the water flows away. So in this figure, it'd be flowing towards you or away from you, and then the blocks on top start to down drop, and that's how you get over here. That's how you get these polygonal mesas and these carved valleys like we're seeing in the fretted terrain. And you can kind of see how that looks similar. So future work, I'd obviously love to go to Mars, but probably not going to happen anytime soon, maybe in the next 20 years, who knows. But in all reality, we're currently working on a Mars Data Analysis Program grant to look at higher resolutions of those cliffs, to see if we can find any higher resolution features that might indicate its origin, either if its origin is related to those super explosive volcanoes that I mentioned, or if its origin is related to something totally different. And I'd also like to test those hypotheses, and I have some ideas for how I'm going to test them, so if you'd like to know, I can talk to you about that later. And this is just an image of the high-resolution cliff faces that I was talking about. And so in conclusion, the processes that form the fretted terrain were not gravity-driven, rather they're driven by fracturing of some sort. And so more investigation is needed into the geometry of these fractures and the geomorphology, which pretty much just means the way it looks, in order to determine how the fracturing got there. And here is my name and my contact information. If you have any questions, I'd be more than willing to answer. And thank you so much for listening to my talk.